I think I'll begin. So what we're going to do today is, what we did this last two lectures that looked at our major evolutionary innovations, the Cambrian explosion that occurred here. We looked at sort of mass extinctions and background extinction. And so what we're going to do today is look at climate change, largely change in temperature from the time of the Cambrian explosion up until the last ice ages. This diagram is weird. It's millions of years here up to 100, and then it goes from about 100 million years to 10, and then it changes scale again from 5 million years to 500 years ago, and then changes scale again, and this is now in just current years. But what I want to draw your attention to is this little blip here called the Little Ice Age. And I'm just going to mention that once, but I wanted to draw your attention to the fact that there was a tiny, tiny ice age in historical time that is an absolutely trivial temperature variation. And that's going to be important in just a couple of lectures from now, a couple of minutes from now. So just remind you that the tours, I think there was one yesterday, and so tours of the museum, so meet at the feet. We actually meet at the wrong end of T-Rex, actually. That was too long to write. So you'll see a lot of the collection today and tomorrow. Okay. And so we're looking now at geological, biological, and astronomical drivers of climate change, largely temperature change. And this lecture is going to go backwards and forwards between myself and Elliot. And so we're going to start off with a question, which is what drives temperature change? And so I've given you 4 options. Changes in the Earth's orbit, changes in the sun's luminosity, changes in CO2 concentration, and tectonic activity, or changes in tectonic activity, or tectonic activity. Sorry? Are you asking, are they related to each other? Yeah. They are. But they can be independent of each other too. We'll get to that. So what have we got? 4 colors, 4 colors, 4 colors, 4 colors, 2 colors. So changes in the Earth's orbit. Elliot will be telling us about that. Changes in the sun's luminosity, and that seems to be responsible for that little ice age that occurred in sort of the 1800s. The Thames River in London froze over. But it seems that this is a really trivial component compared to the others. So it's there, but it's not very big. So I probably should have put it in dashed. And then changes in CO2, which can occur either as a consequence of tectonic activity or of other activities. So that's kind of give you a shape of what the lecture is going to look like. So now diving into each of the components, the first thing I want to do is just actually look at the measured long-term climate or temperature change. Just what does the pattern look like? And then Elliot's going to tell us about the greenhouse effect and then astronomical drivers of climate change, the changes in the Earth's orbit or orbital parameters. And then I'm going to come back and talk about the long-term and the short-term carbon cycles that are very, very different from each other. Okay, so measured climate change. And so here's a diagram showing the change in the sort of the mean global temperature. There's about a 10 degrees Celsius swing. So what's that? I keep on forgetting about 18 degrees Fahrenheit, average change, starting with the Cambrian explosion, where it's particularly warm and it goes up and down and up and down. The blue line is sort of the data and the red line is sort of an averaged. And so you can see that we are today, in fact, at almost an all-time cold. So when we talk about global warming, which we'll talk about in a couple of weeks from now, we're actually at an all-time cool for the planet, which was matched here at the end Ordovician, which is when there was a global glaciation that caused the first great mass extinction in the marine realm that we looked at last lecture. And so what we want to look at is the controls on this large-scale fluctuations. The time of the dinosaurs, it was especially warm. It looks like the Earth was essentially ice-free. No ice at the North Pole, no ice at the South Pole. There are forests and dinosaurs on the northern slope of Alaska, and Alaska was closer to the pole back then than it is now. So a very, very different climate at that particular time, particularly during the mid to late Cretaceous, and then running into this time period here. Okay, so that just gives you the sense that there's been a lot of variation. And so what we really want to do in this lecture is look at the principles that drive that variation. How do we get these numbers? Well, we can't go out there with a thermometer, so we need an indirect measure of it. And so most of these numbers come from fossils. And so these are foraminifera, small protists. Well, actually not that small. Some of them get to be the size of I don't know what that size is. That size. Some of them are the size of a quarter. Most of them are called microfossils. You'll see some in the tours this week. And what we measure is the relative amounts of oxygen 16 to oxygen 18. And it turns out that the enzymes that animals use to build, or organisms use to build their tissues, are sensitive to temperature. And the temperature depends on how much oxygen 18 versus 16 gets incorporated into the cell. And I'm not going to explain how that happens, but it's a fairly standard tool in the geological sciences. And it's got this horrible notation that is only put in here because you're going to see it on the next slide. So the way this operates is these guys build skeletons, some of them out of limestone. So this is a small slab of limestone. There's lots of oxygen in limestone, as well as carbon and calcium, but lots of oxygen. And so the organism discriminates between oxygen 16 and oxygen 18 depending on the temperature. The discrimination depends on the temperature. And so this is the basis of the measurements. But what is interesting is that it makes critical assumptions about the relative amounts of oxygen 18 and 16 in the ocean at the time. And it's hard to get those numbers. And so we don't know whether the curve looks like this or whether it looks like this. So piecemeal, we know it's getting colder and then warmer, but we don't know over 500 million years whether the baseline is shifted in some way. So we don't know whether, in fact, it was generally warmer in the distant past in terms of animal evolution as opposed to the present. And that's an uncertainty that people are working on. So this oxygen isotope data, so there's that horrible notation thing there, which is the fundamental units that's being measured. And then temperature is being inferred from that. And there are other complications like ice volume make a difference. And so then we have a curve here which is better established. This is 65 million years ago. So what happened, or 66 million years ago, what happened then? So we have a question.
For the oxygen 16, which one would you expect to see more of?
I can measure it off here. The colder it is, the more 18 there is. Yeah, it's complicated. It's complicated because sometimes you can measure the organism, sometimes you can measure the rock, which is minus the organism. So usually the higher the temperature, the greater the discrimination, the more, I'm going to get it confused, I'm going to leave it alone. Because there's 2 or 3 competing components and they play off against each other. So here's a diagram with, again, the oxygen 18. I'm not going to explain the notation. And then the inferred temperature here, which is more quantitative. So this is 66 million years ago, which is when? What happened then, 66 million years ago? The death of the dinosaurs, the Chicxulub bolide impact. So it's very warm then. It looks like ocean temperatures got warmer and then steadily cooler. And then we get the first ice sheets occurring in Antarctica, and the temperature drops in this period here called the Oligocene or Oligocene. And then it warms again here, and then slowly and steadily cools as we come to the present. What's also I'd like you to note is that the little black dots are individual measurements from different parts of the world, that as we get closer to the present, the variance starts to go up more and more. So it suggests that there's much more variation, short-term variation with time. And in fact, as we'll see, it's because actually the temperature is beginning to oscillate really dramatically. So the temperature here is relatively stable in one part of the globe to the next, or from one half-million-year interval to the next half-million-year interval. But here, the temperature starts to vary erratically, backwards and forwards and backwards and forwards. Question. So there's the relationship. The question is it also because we have more measurements? And yes, more measurements gives you the capacity to discover more oscillations. But as we'll see, those oscillations are basically the ice ages. And in the last million years, there have been about 10 of them. So we talk about the last ice age. Well, that's the 10th out of about 10 that have occurred. And those are those oscillations. And we'll see the drivers of that shortly. But what I want you to note is that over the last 15 million years or so, the globe has been steadily cooling. And one of the questions which we'll get to in this lecture is, why has it been steadily cooling? What's driving that cooling? And so we'll get to that later in the lecture. So again, here we are at one of the coldest times in the relatively recent geologic past. And then we're in an interglacial, so we came out of a glacial into an interglacial, so it's a little bit warmer than it was, but on average the whole thing is cold. So we can see the expression of this global cooling that occurred over the last 15 million years or so in the fossil record off the coast of California. So here are maps of California with millions of years ago, so roughly 25, and then, I don't know what that is, sort of 20-ish, 15, 10-ish, 7, and 2 or 3. And the colour here is a code for the surface water temperature based on the fossils. And you can see here's the Bay Area up here. That's it there. So we don't have rock of that age up there, but you can see that basically it's really tropical. There's an interior seaway here, and you'll see fossils from there in the museum tours. It's basically tropical all the way up the coast of California. Same about 20 million years ago, and then starting around 15 million years, it starts to cool, indicated by the orange here, and then the green, and then the blue. And by the time we get to the last few million years ago, the tropical waters have now gone all the way down to Mexico and further south, and we now have actually very, very cold waters off the coast of California. And so you can see this contraction of the tropics and this sort of increased steepness of the temperature gradient over this 15 million year period. So it's a very real change that occurred corresponding to this cooling that occurred over 15 million years ago. Question?
So would the organisms that have lived in the water during the more tropical time period off the coast, would they have evolved to live in the colder water, or wouldn't they have migrated down the coast?
That's a very good question. So the question is, as things got colder, would organisms have evolved to adapted to the new conditions, or would they have simply have moved with the warmer waters? And for the most part, they simply move. That's where they're well adapted to, and they simply transport down. It gets more difficult if there's nowhere to move to. And then you expect extinction rates to go up, and those that can adapt do adapt. So that's a good question. So most of it is actually just migration. These temperature bands are actually based on the fossils rather than an independent measure of the temperature. And so we're close enough to the recent that the biology of the living ones is well known, and we can extrapolate back into the past. So it's a very good question. So then I just want to show you then the temperature curve for the last 5.5 million years. And so here are these oscillations, and then here are these oscillations getting larger and larger in magnitude. So it's not just more data, it's the fact that the temperature variation got more and more extreme. And so here it's particularly extreme in this last million years are the roughly dozen or 10 major ice ages that we've experienced. And we're currently in one of the relatively short-lived interglacials, indicated by the blue here. But most of the time was actually spent in ice age time. And so if we wind back the clock just 50,000 years ago, this is what we think the world will have looked like, which is rather extensive extensions of the ice sheets of the northern hemisphere compared to now, where there's relatively little except in Greenland and Arctic Canada. Okay, so that gives you just a very crude sense of what the temperature trajectory looks like over the 500 million years. And so now what we want to do is look at two of the primary drivers, which is the greenhouse effect, its relationship to CO2, and then the changes in the orbit of the Earth, which seems to be also important, particularly for the ice ages. And so the greenhouse effect is now.
Okay. So we've talked about different aspects of stellar and planetary systems that determine how likely a planet is to be habitable. So a couple of the ones we've talked about are the property of the star. So a star like the Sun produces a lot of heat for planets on orbits like the Earth, and so you can have liquid water. If you go to a much smaller star, much lower mass star, they're much fainter, they give off a lot less heat. So a planet out where the Earth is would be frozen. It's only a planet much closer in that would actually be hot enough, heated enough by its host star to have likely habitable conditions. And so these are some examples of where the likely habitability of a planet depends on the properties of the star, where the planet is. We'll see other examples of what determines habitability as we go through the rest of the course. One of the things we know from our own solar system, though, is that this simple picture of going further away means you're getting cooler isn't true, because we can just look at the measured temperatures on the surfaces of the planets in the solar system. And if you do that, what you notice is that actually in general this story is true. Further away, things get colder. Mercury here is much hotter than the Earth, which is hotter than Mars, which is hotter than Jupiter, Saturn, Uranus, Neptune. So that sequence works pretty well, except there's a big dramatic outlier, which is Venus. So Venus is substantially further away from the Sun than Mercury is, but its surface is also substantially hotter than any of the other planets in the solar system. And this turns out to be due to the very unusual atmosphere that Venus has. And so an important part of the story of what determines the temperature of a planet, and thus we think how likely it is to have water, how likely it is to have biological processes, is what actually is the atmosphere of that planet. And so the story of Venus and why Venus is unusual in the solar system relative to the other planets is actually a story about the greenhouse effect and the effect of the greenhouse effect on the surface temperature of Venus. So to remind you just first from everyday experience what the greenhouse effect is, so the greenhouse effect is you're in a car on a sunny day, windows are rolled up, it gets extremely hot in the car relative to the outside ambient temperature. That happens not only in a car, but in the aptly named greenhouse. Right, so that's why you grow things like strawberries in coastal California. In greenhouses, it can be cool on the coast, but you put them in a greenhouse, the temperature goes way up. You get conditions that are actually much better for growing certain types of plants. And this effect, the greenhouse effect, has to do with what happens to light from the sun as it hits the surface of the Earth, or as it hits things on the surface of the Earth, like greenhouses or cars. So to remind you, the sun, right, emits mostly visible light in the visible part of the electromagnetic spectrum. That light, as it travels towards the Earth and starts to interact with the surface of the Earth, several different things can happen. We talked about these basic ways that light interacts with matter earlier in the course, and so now we're going to apply them to light from the sun hitting stuff on the surface of the Earth. So one thing that can happen is that light from the sun is just directly bounces off of, it reflects off of, either the atmosphere of the Earth, so clouds reflect sunlight. Similarly, ice is very reflective, water is very reflective, and so you can have light from the sun simply get reflected off of stuff in the atmosphere of the Earth, or rocks, or water, or ice. But you can also have the light actually get absorbed by the material, by the molecules that make up the car or the ground, and heated up. And so the way you actually heat up the surface of the Earth is not by reflection. That just sends the light back out the same as it came in. The way you heat up the surface of the Earth is by absorbing the light of the sun. And what happens then is that absorbed light heats up the surface, and the surface of the Earth, we know, it radiates its own energy. The surface of the Earth at temperatures of 70 degrees Fahrenheit, a few hundred degrees Kelvin, radiates thermal radiation primarily in the infrared. So remember, what we see with our eye when we look around is entirely when we look at stuff on Earth, it's entirely reflected light. The actual light that's being radiated due to the heat of objects on the Earth is primarily in the infrared. Okay, so you can see that with infrared goggles, not with your eyes. And the greenhouse effect is really fundamentally about what happens to this thermal infrared radiation relative to what happens to the incoming visible light. And the basic idea is that under certain conditions, this thermal infrared radiation that's trying to go back out, that's trying to be radiated back into space, it can actually get trapped. That heat that's trying to get radiated away can get trapped, and it can go into dramatically increasing the temperature rather than simply being radiated into space. And so what happens in a car is that the visible light from the sun comes in, it gets absorbed by the tapestry, by the dashboard, which is usually a dark color, so it absorbs very well. And then it tries to get re-radiated back as thermal infrared radiation back out into space. But the glass, in particular, and the roof of the car doesn't let infrared light go through very effectively. And so the infrared light that's trying to get out instead gets trapped as heat in the car. And that causes the temperature to go up. And that's really the fundamental origin of the greenhouse effect, is that some of the visible light coming in can't get radiated back out as infrared light. It gets absorbed and goes into really heating up the interior of the car or the interior of the greenhouse. So that's the basic mechanism, this trapping of infrared light and heat that raises the temperature of objects. So that's what happens in a car or in a greenhouse. And exactly the same thing can happen in a planet depending on the properties of its atmosphere. So if we think now about a planetary atmosphere and try to think about the greenhouse effect in that context, so visible light comes down, some of it bounces off, is reflected, some of it is absorbed, and then depending on what the atmosphere is made of, that infrared light can have a lot of trouble getting back out again, so it can get trapped by the atmosphere itself. When that happens, when the atmosphere traps the infrared light, the temperature goes up on the surface of the object, and so you end up with a much hotter condition than you would have had if you didn't have this atmosphere trapping the infrared light. And what turns out to be particularly important at trapping infrared light is molecules like carbon dioxide, methane, water vapor. So those molecules, which are generally called greenhouse gases, so gases that contribute significantly to the greenhouse effect, right? Those are actually the stuff in the atmosphere that traps the infrared light, stops it or slows it down from getting out, and so builds up the heat and increases the temperature on the atmosphere. And so when you think about the temperature on the atmosphere of the Earth or other planets, possible alien civilizations, etc., one of the factors that's actually critical in setting the temperature of the surface of the planet is exactly how much of these greenhouse gases are there. How much CO2 is there, methane, water vapor, etc. Those all contribute significantly to setting the surface temperature of the planet. And so that's part of what you're seeing in these histories of the surface temperature of the planet that Charles showed, these variations in temperature are affected to a very large extent by changes over millions and hundreds of thousands of years of the amount of greenhouse gases, CO2, et cetera, in the atmosphere. So these variations, hot to cold on hundreds of millions of years timescales, are regulated to a significant extent by variations in the CO2 content of the Earth's atmosphere. And it turns out that the same is true for Venus. So the remarkable thing about Venus is that it has an atmosphere that is 100 times thicker than the atmosphere of the Earth. Its atmosphere, the gas in the atmosphere of Venus, has 100 times the mass of the atmosphere of the Earth. And that atmosphere is almost entirely carbon dioxide. And so that produces a whopping greenhouse effect on the surface of Venus. And so Venus, despite being significantly further away from the sun than Mercury, is actually the hottest object in the solar system, or the hottest surface in the solar system, because of this extraordinarily thick atmosphere of greenhouse gases that raises the surface temperature of Venus and makes it this extraordinarily inhospitable place that it is today. So, any questions about that? Okay. So the story of how Venus ended up like this, how it ended up this kind of inhospitable furnace, is actually a very good lesson for thinking about the climate of the Earth, the climate of other planets, and actually the potential future of the Earth. So just to remind you, we think in the distant past, 4.5 billion years ago, when the planets were forming, the sun was significantly fainter than it is today, something like 30% fainter. And it was actually sufficiently faint that at least the simplest models of Venus predict that at those early times, Venus was a much more interesting surface than it is today, and it may have actually had substantial oceans. The sun was fainter, Venus was cooler, and so it may have been cool enough that it could actually have liquid water on its surface. But as time went on, as the sun got hotter, remember the sun gets hotter, driven by the change in what the sun is made of, from hydrogen to helium. As that happened, Venus underwent a dramatic change in the nature of its atmosphere. And what we think happened is actually a runaway greenhouse effect at some point set in. In particular, as the sun's luminosity went up, eventually the surface of Venus got hot enough that the water would start to evaporate. That would put water vapor into the atmosphere of Venus. Water vapor is a greenhouse gas, so that would increase the temperature by having more water vapor in the atmosphere. The higher temperature on the surface of Venus would mean more evaporation of the water. That would mean more greenhouse gases, which would mean a higher temperature. And so you have the process of a runaway where you get this dramatic increase in temperature, which leads to the evaporation of the liquid water on the surface of Venus, and eventually all of the water going into water vapor in the atmosphere. Then as time went on, actually we think most of the hydrogen in the atmosphere actually evaporated even off the planet. So the hydrogen leaked out, leaving behind the oxygen in the atmosphere. Carbon in rocks eventually made its way into the atmosphere by the kinds of processes that Charles will talk about at the end of this lecture, kind of long-term carbon cycle. And so what was left behind is an atmosphere primarily of CO2, where the kind of there's not much remnants of the water vapor left today. The hydrogen is all gone. The oxygen is bound up in carbon dioxide. So that story is a useful warning lesson or a useful lesson about the history of the Earth's climate. Just to give you a sense of this, if you took the Earth today and you moved it into where Venus is, we think exactly the same kind of catastrophic runaway greenhouse effect would happen. The Earth, if it was closer to the sun, that would try to make it hotter because of the extra heat from the sun. That would evaporate the water, etc. So the same story about a runaway greenhouse effect would happen if the Earth were placed closer to the sun. Now, yep? Right. So the question is, would the nitrogen and oxygen actually eventually dissipate? Would you end up mostly with CO2? That's a good question. I don't know the answer. Charles, do you know?
No.
Yeah. So I don't know exactly whether something similar would happen, that you would lose the nitrogen and oxygen. I think not. The reason you can lose the hydrogen is that once the water is broken down by ultraviolet light from the sun, then you're left, in Venus's case, with oxygen and the hydrogen is light enough to actually escape the gravity of Venus. The oxygen and nitrogen molecules are not light enough to leave the surface of the Earth, so I don't think you would end up with quite such a concentration of CO2, but I'm not certain of that. So, right, the question is, why didn't something similar happen to Mercury? So Mercury is so close and so small that it really never had much of an atmosphere. And so it didn't go through an analogous process with it. Yes, great question. So it's not just this kind of thought experiment of moving Earth closer into the sun that leads to a runaway greenhouse effect. Remember, we think the sun is getting brighter as time goes on, and so in the future of the Earth, the sun will be brighter. And in fact, in about 1 billion years or so, give or take probably 500 million years, the Earth's oceans will evaporate, and we may have this kind of runaway greenhouse effect, not simply due to the increasing brightness of the sun, increasing the temperature of the Earth. It's actually a little bit worse than this. One reason that people are worried about climate change and the increasing amounts of carbon dioxide that we're putting into the atmosphere of the Earth is that there's the potential for this kind of catastrophic runaway to happen, not due to the increasing luminosity of the sun on billions of years timescales, but rather the increasing amount of greenhouse gases, in particular carbon dioxide, that we are putting into the atmosphere of the Earth by burning fossil fuels. And that's something we'll come back to a few lectures from now when we talk about the impact of humans on the Earth. Yep?
But since we're in a particularly cool time for the Earth, even if the atmosphere changed by a couple degrees, when it still goes back to where we were?
Yeah, so a couple degrees. So the question is, since the Earth is relatively cool now to what it is in the past, it's true that a few degree change in temperature, while very problematic, causing sea levels to rise, all kinds of other problems, freak superstorms, you name it, right? It's true that that alone would be unlikely to trigger this kind of runaway. Only if things got much more extreme than that would you have this kind of runaway. That's exactly right. So you would need tens of degree change in the average surface temperature. Yeah. Okay. So that's a little bit about the greenhouse effect, and in particular the role of greenhouse gases via the greenhouse effect in regulating the temperature of the Earth on long time scales. What I want to talk about now is kind of the remarkable role that seemingly small changes in the orbital and spin properties of the Earth have in actually producing dramatic changes in the climate of the Earth. And this is really a story about understanding the variations in temperature and carbon dioxide concentration that are seen in the geologic record over the last 400,000 to 1 million years. And so when you look at this, so this is concentration of CO2 in the atmosphere, and this is the inferred temperature from the oxygen abundances, oxygen 16 versus oxygen 18, in the past. And so what you see when you look at this is that there are large variation, tens of degree variations in temperature, but they seem to have a kind of regularity associated with them. There's kind of regular variations on hundreds of thousands of years, producing these peaks and troughs. And then there's variations more like on tens of thousands of years timescales. And so the question we want to address, and this is really, I should say, this is the ice ages, right? The colder regions are the ice ages. And so the question is, what produces these variations? So first, I just want to mention, how do we actually know this? This is a really cool technique for measuring directly through the geologic, quote-unquote, record what the temperature is. And it actually comes by measuring ice in very icy places like Antarctica. So this is a picture of Lake Vostok. Does that look like a lake? Does anybody know why it's called a lake? I had to look this up, actually. So it turns out if you go under the ice, it's liquid water. So geothermal heating from the interior maintains beneath this very thick layer of ice, actually maintains water in a liquid state. And so that's why this is called a lake. There's a bunch of kind of lakes like this, even in places that you think of as completely frozen. So, yep. So the question is, have they found life in these lakes? Great question for a biologist. I don't know the answer. Anybody?
I think they have. They've been talking of drilling it, and then they've got concerned that if they drill it, they'll contaminate it. And so there's this dilemma of how do we look into it without actually bringing life down to the root cause?
Yeah, so that's a great question. One of the things we'll talk about in a few weeks is what places in the solar system are actually the most likely to have life in addition to the Earth. And one of the most promising, kind of surprisingly it turns out, are some of the moons of Jupiter, where although on the surface things are frozen, there are lakes underneath. So it's a very similar situation to this. So what people do is you actually go and measure, you take ice cores out of the ice, so very long, kind of rod-like distributions of ice, and these ice cores have in them a record of the climate over the last million or so years.
400,000.
400, yeah, I thought.
That's the reason why the graph stops at about 400,000.
So in Vostok, it's 400,000. I think there's some other place where it goes up to 800,000, I thought. So, okay. So these ice cores do a couple of things. They trap, in particular, gas bubbles, and those gas bubbles have the concentration of CO2 and the concentration of the different isotopes of oxygen, and so they allow you to infer both the carbon dioxide concentration of the atmosphere and the temperature of the atmosphere over the past 400,000 years in the case of Lake Vostok. And in particular, the really cool thing is that because the snow never melts, you actually get yearly patterns in the ice, so you can read off what year a given place in this ice core corresponds to, just like you read off the age of a tree from its tree ring. So each of these arrows represents a particular summer where the ice has accumulated in a layer that has a characteristic thickness and a characteristic color. So these are all the summers, and then in between are all the winters. So you can literally read off this yearly climate pattern going back in these ice cores. It's really quite a beautiful measurement that allows us to do this quite exquisite and detailed inference about the climate history over the last 400,000 years in this case. So that's how we actually infer this record of the variations in climate and CO2 concentration. And so what I want to do now is explain to you why this pattern exists, why there are these rather dramatic variations associated with the ice ages, in the temperature and CO2 concentrations over the last 400,000 years. And to do that, I have to remind you why the Earth has seasons. So the Earth has seasons, remember, because of the moon, indirectly. So the collision that produced the moon produced this 23-degree tilt between the spin axis and the orbital plane of the Earth. So the Earth is spinning, and the direction of its axis is not exactly perpendicular to the orbital plane of the Earth around the Sun. Rather, the spin axis points about 23 degrees away from that perpendicular to the orbital plane. And it's that tilt that actually dominates today the origin of the seasons. So in particular, what happens is that in a situation like this, where the spin axis is tilted kind of away from the sun, this is a region where in the southern hemisphere is oriented a little bit more towards the sun, so it gets some extra heat, and that's what we call summer. By contrast, at this time, the northern hemisphere is pointed a little away from the sun. It gets a little less heat from the sun, and so that's what we call winter. So this time in the orbit is roughly December, so it's pretty close to now, right, where in the northern parts it's a little cooler, in the southern parts it's a little warmer. As the Earth orbits around the sun, say as it ends up here, now in the northern hemisphere is tilted a little bit towards the sun, and so it gets a little bit more solar heat, and so it's a little warmer. That's our summer. By contrast, in the southern hemisphere, Australia, etc., now those regions are pointed a little bit away from the sun, so they get a little less extra heat. So they're a little cooler. That's the Australian, New Zealand winter. And so that's kind of the origin of our seasons, due primarily to this tilt in the spin axis relative to the orbital plane. And the amazing thing is that this number of 23 degrees turns out to vary in time. It's not a constant. It changes over tens of thousands of years. And in particular, it changes by what seems like a kind of insignificant amount. It changes from about 22 degrees to 24.5 degrees. So it's today about 23 degrees, but on time scales of tens of thousands and 40,000 years, this angle changes by this small amount. And that change is actually due to the effect of the tides from the moon and the tides from the sun kind of pulling on the spin of the Earth, changing this tilt a little bit. Yep?
You said that the tilt of the Earth is today primarily responsible for seasons. Are there other factors?
Yeah, I'll come back to that in just a second. The question is, are there other factors? There are other factors that contribute to variations in kind of solar heating over the year. I'll come back to that in just a second. And so what happens then, due to the moon and the sun kind of pulling through tides on the spin axis, that causes this tilt to change in time. And the effect that that has on the seasons is kind of what you'd expect based on the explanation I just gave you. If the tilt is a little bit less, so the angle is smaller, you have less extreme seasons, so the summers are a little cooler, the winters are a little warmer. If the tilt is bigger, you have more extreme seasons. You have warmer summers and cooler winters. And in particular, the less extreme seasons, the smaller tilt, is actually associated with the ice ages. The cooler summers means that the ice doesn't melt as much, so it builds up more effectively. So when the ice is able to build up more effectively, you build up larger ice sheets, and hence the ice ages. So the ice ages are associated with these times of somewhat smaller tilt. And in particular, the tilt varies with a period of about 40,000 years. set by the kind of strength of the tides of the moon and the sun acting on the Earth. And so some of the periodic variation you see here, timescales of 40,000 years or so, is due to this variation in the tilt. It turns out the direction of the tilt also precesses, kind of like when you spin a top. The top doesn't spin in the same direction. It's kind of wobbles about its axis. That's called precession of the axis, that wobbling. And the direction that the Earth's spin axis is pointing in changes not just in the angle, but also in the direction it's pointing. That has a period of about 26,000 years, meaning it goes in a circle over about a time scale of 26,000 years. And that also contributes to this variation in the climate on tens of thousands of years time scale. So there is another effect that contributes to long-term variations in climates, as the question just asked, and that's that the Earth's orbit becomes more eccentric and less eccentric as time goes on. In particular, the effect of the gravity of Jupiter and Saturn on the Earth's orbit causes the eccentricity to change from what it is today, which is about 0.017, to a value that's smaller, about 0.005, to a value that's larger, about 0.06, with a period of roughly 100,000 years or so. So the orbit goes from being more circular to being more eccentric due to the action of the gravity of Saturn and Jupiter. And that change in the shape of the orbit, when the orbit is more eccentric, there are larger differences in the amount of sunlight received when the Earth is close to the sun and far away from the sun. And so changes in eccentricity produce yearly variations in the amount of sunlight. So today, right, if you ask people, the common answer for people who haven't taken a course like this, or a high school science course, is that the seasons are produced by differences in distance between the Earth and the sun. And that's not really true. Today, given the orbit of the Earth, the primary cause of the seasons is this tilt in the direction of the Earth's spin. But when the orbit of the Earth is quite eccentric, when the eccentricity is larger, the orbit is more elongated, then there are about 25% differences in the amount of sunlight from the time in the Earth's orbit when it's closest to the sun and the time in the Earth's orbit when it's furthest from the sun. And those 25% differences in the amount of sunlight hitting the Earth actually produce large temperature changes. So to remind you, this whole business about the faint young sun, the fact that the sun was fainter in the past, and that produces, possibly oceans on Venus and cooler conditions on the Earth. That faintness of the sun corresponds to a difference in sunlight of about 25%. So a 25% difference in sunlight is actually a really big effect. That's about a 50-degree difference in the surface temperature of the Earth. So that difference, due to the eccentricity of the Earth's orbit, when it's more eccentric than it is today, can actually have a pretty big effect on climate. So the combined effect of these variations in... Go ahead.
So wait, just to clarify, the eccentricity is caused by the Jupiter and Saturn's gravity?
Yes. So Jupiter and Saturn's gravity slowly changes the shape of the orbit of the Earth by, very slowly. It takes 100,000 years for the shape to get more eccentric and then less eccentric and more eccentric and less eccentric.
Why would it? I don't understand. If the gravity is constant, why would it vary? Why wouldn't it continue?
Right. So the question is, since the gravity seems to be, the orbits are kind of the same, what is changing that causes it to go back and forth and back and forth? So it turns out that as planets orbit around each other, there are special there are special times when the gravity of Saturn, say, acting on the Earth, accumulates and becomes more effective. And then there are times when the effect of Saturn's gravity doesn't accumulate and has less of an effect on the orbit of the Earth. And this has to do with the exact ratio of Saturn's orbital period to our orbital period.
But I mean, at heart, the issue is that, sometimes Jupiter and Saturn are on the other side of the Sun, sometimes they're on the near side, sometimes they're next to each other, sometimes they're on the other side of the Sun with respect to each other.
So in alignment, they...
Well, I don't know what the details are, and it's complicated.
Yeah.
What I'm going to say is that the position of the Sun and Saturn and Jupiter and the Earth varies through time. Because their year is a lot longer than our year, so they take a lot longer to go around.
That's right. Now, their year is still, tens of our years. So how you get to 100,000 years from that is more subtle. But the general effect is that on long time scales, small differences in the gravity of Saturn and Jupiter build up, making things a little more eccentric, and then they kind of the effect goes away, and then it builds up again, and then it goes away. Yep. Question?
What do the effects of really large?
The question is, what do the effects of very large earthquakes do? So very large earthquakes do change a little bit the spin of the Earth, right? Every time there's a really big earthquake, you'll read something in the paper about how the spin period of the Earth changed by a nanosecond or something small like that. I think that has a completely negligible effect on climate relative to all of these issues. So that does produce some change, but it's a completely negligible effect. Okay. Go ahead.
How regular is the change?
Yes.
Yeah, so the question is, how regular is the change? So the reason I wrote kind of every roughly 100,000 years is that there's actually multiple time scales, but they are quite regular. So the effect of Jupiter and Saturn together produces periodic changes in eccentricity. So it's a very regular, more eccentric, less eccentric, more eccentric, less eccentric. It's not one time scale. It's several time scales, several periods involved that are all about 100,000 years. But it actually is relatively regular. Yep?
How do we know the shape of Earth's orbital path?
Good question. So the question is, how do we know the shape of the Earth's orbital path? So I think we have no direct evidence for what the shape of the Earth's orbit is. We have indirect evidence by its effect on the climate. Okay? But the way we really know it is that we understand Newton's theory of gravity, and so we can rewind the history of the solar system incredibly accurately. Actually, not just 100,000 years in the past. We can rewind it 1 billion years in the past. And so we can work out the orbits of everything into the distant past. And that physics is so simple and so well understood that we can do it with incredibly high accuracy. And so that's the real reason we have confidence in this set of inferences. Yeah, good question. Okay. So this shows kind of putting this all together and looking at the effect of variations in the direction of spin of the Earth. That's this angle, which is varying from a little over 21 to something like 24 degrees with time. So this is time here in the past 700,000 years and then going into the future. This is the variation in the eccentricity of the Earth's orbit with time again. So the eccentricity axis is here. The spin axis is here. And then what is shown here is the average amount of solar heating, the amount of heat absorbed by the surface of the Earth on average as a function of time. And so what you see is that these variations in spin direction and eccentricity together produce these periodic variations in the amount of heat from the sun hitting the Earth. And that is what fundamentally drives the variation in climate over the last million years or so. These variations are together known as the Milankovitch cycles, named after a Serbian mathematician and engineer who kind of worked out the changes in the Earth's orbit in the past and their effect on the climate. And so the fundamental driver then of the variations in temperature that we see in the geologic record over the last 400,000 years or so is actually the variations in the spin and the orbit of the Earth. It's not actually the carbon dioxide content of the atmosphere of the Earth. What fundamentally drives the variation in temperature is these orbital and spin changes. What happens then is as the temperature gets hotter, say, that releases more carbon dioxide into the atmosphere, that produces more greenhouse effect, and that makes the temperature even hotter. So the importance of the greenhouse effect over the last million years or so is that it exacerbates, it makes more dramatic the variations in temperature with time. But the fundamental cause of the variations in temperature with time is actually these variations in orbit and spin of the Earth. So there's this beautiful correlation between carbon dioxide content and temperature, but the kind of mechanism behind that is a little bit subtle. It's actually variations in spin and orbit causing variations in temperature, which then cause variations in carbon dioxide content, which then cause more or less greenhouse effect and hence more or less significant changes in temperature. Yep?
The variations in spin and orbit cancel out the variations in CO2?
Right. So the question is it possible that in principle what could happen is that the variations in heating due to the variations in spin and eccentricity, could that in principle be exactly canceled by the greenhouse effect, leaving a perfectly constant temperature in time? That doesn't happen. The question is, could it in principle happen? So I think our understanding of kind of long-term carbon dioxide cycle, the long-term carbon cycle on the Earth, is that the variations, as the temperature gets hotter, that does tend to release more carbon dioxide. So it tends to make these variations in temperature more dramatic rather than less dramatic. I don't know if Charles wants to add anything.
Yeah. There's so many factors that it's hard to get it to zero out perfectly.
Yeah, I mean that's a great question, though. Yes, what we do see, I'll just kind of reiterate what we do see. Where we can measure it and try to understand it, the effect of carbon dioxide really is to make it worse, to make the changes in temperature more dramatic, not less dramatic. Yep.
If we didn't have that tilt, we would have already gone through the runaway process.
If we didn't have the tilt in the spin direction, would we have gone through a more dramatic runaway?
No.
I think things would have been more stable, actually, because it's the tilt that produces kind of variations in temperature. So I think things probably would have been more stable. I'm not sure what would have happened if our spin axis had been like much more inclined. We would have had much more dramatic seasons. That's kind of a more extreme case. I'm not sure what would have happened in that case. Okay, great questions. So, So this then shows the actual pattern, the distribution of ice over the last 20,000 years, showing the variation in surface ice caused over the last 20,000 years by the change in the tilt of the Earth's orbit. So this is really the transition from the last ice age to the present day. This phenomenon of the ice ages, as Charles already emphasized, is mostly a polar phenomena. You can see there's the variation in ice content in the northern and southern hemispheres. There's a little bit of change in the kind of coastline at lower latitudes, but the ice ages are primarily a polar effect. In addition to changing the amount of the ice sheets, they also produce changes in where the coastlines are. It's kind of quite dramatic in a place like Great Britain, where today the coastlines are shown in brown. So where the continent is, or where the island is, really is shown in brown. Where the island was in the past is shown in green. So you get quite dramatic changes in the height of sea level, and hence in where the coastlines are. And this actually shows up directly in the geologic record, and that's something that Charles is going to talk about.
So I just want to sort of show here that it's quite common in rock record to notice that the rock units sort of, they're called rhythmites. They go backwards and forwards between one rock type and another, backwards, forwards, backwards, forwards, backwards, forwards. And so this actually is picking up those Milankovitch cycles, those changes in the climate, backwards, forwards, longer summers, shorter summers, longer summers, shorter summers, hotter summers, cooler summers, hotter summers, wetter summers, drier summers, etc. And so we see it in the rock record quite commonly. And so here's actually some rock units here, picking up the cycles in here. This is in the Grand Canyon. And I'm going to zoom in. I have trouble seeing here. So there's somebody for scale. I see this white unit and this white unit and this white unit. So there's a really thick deposition, but the climate we're picking up in the different subtle rocks that are being deposited, sometimes they're very thin. And so you can see, again, this oscillation, and if we zoom in. So the rock record, if you look carefully, turns out to be dominated by these Milankovitch cycles. And one of the tricks is, which one is it? Is it the 41,000-year cycle or the 110,000-year cycle? There's a 400,000-year cycle. There's a 200,000-year cycle. There's a 23,000-year cycle. There's a 26,000-year cycle, as they all interact with each other. And so getting the absolute time is a little bit tricky. And different times in Earth history are dominated by different cycles. So what I want to do to finish off with, question, yeah?
I was going to ask if you go back to the other slide so we can see more again.
That's cruel. So one of the interesting things on the ice cores is that the temperature change precedes the CO2 change. And that's partly why we know it's the Milankovitch that's driving it and the CO2 is responding. But what controls long-term temperature change? This is shorter-term temperature change, but what controls longer-term temperature change on the timescales of tens to hundreds of millions of years rather than tens to hundreds of thousands of years? And so now what I want to do is look at the long and short-term carbon cycles. And so this is the short-term carbon cycle. This diagram is kind of complicated. It actually isn't in principle. It talks about the transfer of carbon from the atmosphere, CO2, to the oceans where it dissolves, becomes bicarbonate, to life, organic material, and soil. And so the short-term carbon cycle is about the transfer of carbon between these reservoirs. So river transport takes soil into the oceans, and photosynthesis takes atmospheric CO2 and turns it into trees, or plants or grass, for example. And so most people, when they get taught the carbon cycle, get taught this as the carbon cycle. The rates of transfer is between sort of days to tens of thousands of years. So the rates vary. Obviously, a big flood is in the time scale of, a year or so or 100 years, depending on the magnitude of the flood. And so I want to now look at the amount of carbon in the short-term carbon cycle. And so what I've done here is this is the terrestrial biosphere, and I've set the amount of carbon to 1. It's, I've forgotten how many gigatons of carbon, and that number's too hard to deal with. Where is most of that carbon? Question, where's most of the carbon in the terrestrial biosphere? Ants, mushrooms, humans. It's almost exclusively in trees. Think of the amount of carbon in giant forests. So this is basically a measure of the carbon in trees and vegetation. Animal life is relatively insignificant compared to the vast forests of the world, particularly places like the tropical rainforests. So the amount of carbon in the atmosphere compared to the amount of carbon in trees mostly is... I'm going to go to the marine biosphere, The marine biosphere has hardly anything in it. So whales are big, but there are not many of them, and plankton is tiny. So most of organic carbon sits in the forests. So that's been critical to the long-term history of the planet, which we will get to. The amount of CO2 in the atmosphere is about 1.2 times the amount of carbon in forests in life. The amount of CO2 up there is about the same as the CO2 trapped in trees, animals, plants, etc. Soil carbon is about 6 times that. So trees die, etc., and the carbon can just get buried by leaves, by roots, by trees. So the amount of carbon in the soil is about 6 times that. So it's partly why people are worried about melting of permafrost in the high Arctic, because there's a lot of carbon buried in the permafrost. You don't want to release that because you could, double or triple CO2 if all of that got released. A lot of it's in the rainforest too. Organic dissolved carbon in the ocean is 56. So as we increase CO2 content in the atmosphere, a lot of it finishes up in the ocean, which changes the acidity, and that's sort of ocean acidification. So a lot of it's in the ocean as dissolved carbon. So those are the reservoir sizes for the short-term carbon cycle. So now what I'm going to do is shift gears to the long-term carbon cycle. And the long-term carbon cycle includes carbon going in and out of rocks. And we don't think about it very often because that rates of transfer is really slow. It takes, in the order of tens to hundreds to millions of years. But the question is, how much carbon is stored in rocks? So we've seen the relative numbers there. So, 1% of the living biota, about the same as forests, about 100 times living biota, about 10,000 times the living biota. So what are your guesses as to how much carbon is trapped in the rock record? So we've got some greens at about 100 times. We have some reds at about 10,000 times. Anything else? Whoops, right. Yeah, so the answer is a lot more than 10,000. I cheated. Organic carbon in rocks is about 25,000 times. So that's coal and oil. 25,000 times as much as there is in the forests. The amount of carbon in rocks and things like limestone is 100,000 times. So the reservoirs in carbon in the rock record utterly dominate the reservoirs in the oceans, in the soil, and in life, and in the atmosphere. So if you can change the rate at which you release carbon from the rock record, you can dramatically change CO2 levels. Incredibly so. And so it turns out on human timescales it's not so important because we only transfer amounts of carbon in the order of about 1% per million years. So the transfer of carbon to and from rocks is important because of the huge amount of carbon. Transfer is very slow. In 100 years, only about 100% of the carbon in the atmosphere is transferred to and from the rocks. So 100 years of volcano eruptions only adds about 1%. So on human timescales, the long-term carbon cycle is essentially irrelevant. But on timescales of 100 million years, or 10 million years, then it starts to make a difference. So about 1% of CO2 is pulled out of the atmosphere by erosional processes. About 0.5% to 1.5% is put back into the atmosphere by geology. And so now we're going to get to the importance of tectonics. And so I showed you this before, but I didn't show you the commentary. Pardon the funny accent.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart. And it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption.
So what's critical, it's not just fossil material, but also if limestone goes down. It also, of course, comes up as CO2. So what happens then is limestone and fossil material goes down, comes up as volcanoes into the atmosphere, and then the CO2 interacts with water vapor, where it dissolves, interacts with rocks, where it gets precipitated as limestone. And so that's the long-term carbon cycle. Carbon coming out of the rocks and then carbon going back into the rocks again. And so one of the interesting questions is if you turn the carbon cycle off, if you turn plate tectonics off, what happens? If you turn plate tectonics off, you still get CO2 interacting with rainfall and getting turned into limestone. And it turns out that without tectonics, all the CO2 in the atmosphere would be scrubbed from the atmosphere in about 10,000 years. Now, there's a lot of CO2 in the ocean, so that would degas into the atmosphere, which would then get turned into rock again. So after 300,000 years, roughly, there would be no CO2 in the atmosphere. Period. Pretty hard to make plants if there's no CO2 in the atmosphere. So we would be a dead planet if it weren't for plate tectonics. So the long-term carbon cycle is critical to the existence of life on the planet. Without it, there would be no life because there would be no CO2 in the atmosphere. Question?
Could we hypothetically replace tectonics by the amount that we burn things which are carbon and release carbon in the atmosphere?
Yeah, so we're going to get to that. So we...
And we just kept doing what we were doing, would it be cool?
Yeah, so if tectonics switched off, we could just burn coal and oil and put the CO2 back in until we deplete it completely. Yeah, so we could do that for quite some time. So yes, we could do it. But what it suggests is this finding has radically changed the way we think about the importance of active tectonics for the likelihood of life on other planets. What it says is you probably need to have an active tectonic system so you can recycle things like CO2 so you can sustain life elsewhere. So this becomes critically important. So tectonics has raised its head again now in terms of the fundamental habitability of planets. And that's really critically important. Now what I want to do is, I think I'm going to try to rush this. I ran out of time, but I want to rush this, which is, here is a diagram of the amount of CO2 over the last 600 million years or so. The units here are in total amounts of CO2 in the atmosphere. So 1 is the current level. Humans have increased that by about 10 or 20%, so 1.2. But in the past, it was 15 to 20 to 25 times higher. So incredibly higher than it was in the past. And we're sitting here at this all-time low sitting here. But what I want to look at is this incredible drawdown of CO2 that occurred after the Cambrian explosion. And the question is, what caused that drawdown of CO2? And interestingly, it corresponds to the evolution of the first forests and the first leaves in forests. And so what seems to have happened there, if we look at the transfer of carbon between trees and the atmosphere, it looks like this. CO2 is drawn down by photosynthesis into trees. And what typically happens on the biosphere, producing CO2, is that animals, fungi, take the CO2 and respire it, breathing out CO2, right? and out goes CO2. And that's just a cycle. If every plant that died rotted and got respired back out again through us, we'd have an equal balance. But once you grow big trees, you can bury big trees, which means you can bury carbon. And when you bury carbon, there's less of it to be respired back up into the atmosphere. And so you drop CO2 and you also build up oxygen because you don't respire as much. So once you get the first great forests, you can bury large amounts of carbon, which means you don't return the CO2 back to the atmosphere. So the CO2 is taken out of the atmosphere and pulled down into the soils, into rocks. And that's what we're doing now, is we're burning it and putting it back again. And so it looks to us what's happened. Yes, I'm going to skip that. Yeah, well, so here's, the drawdown of the CO2, and here's the increase in oxygen we see. And the increased oxygen seems to be responsible for these enormous arthropods that occurred in the great coal forests of the Carboniferous. Giant insects, giant dragonflies, etc. So that evolution of the forest seems to have fundamentally changed the carbon balance in the atmosphere. And so what's interesting is this time corresponds to the end Devonian mass extinction. And so I said last lecture that I think the end Devonian mass extinction may actually be an indirect consequence of the first forests that cause massive global cooling as the CO2 gets drawn down and massive increases in the oxygen. And so the late Devonian mass extinction is sitting in this phase here. So it looks like the forest may have had a major impact in the way the biosphere operated. And so, with a minute to go, what we're going to do next lecture is look at the emergence of humans and how we settle the Earth. This is Ardipithecus, discovered by Berkeley professors. And, Berkeley's an amazing place, but you get some mega professors, and one of them is Tim White here. And he will be lecturing on Tuesday on the discovery and the roots of Homo sapiens from the fossil record. And he's already said that he's going to tease the heck out of me, so I'm a bit nervous about what he's going to say. And then the next lecture will be by Leslia Hlusko, also from Integrative Biology, who'll be talking about how humans settled the Earth. And in section next week, you'll be looking at how we use DNA data in particular to work out how we colonized the planet in prehistorical times. Okay, there you go. Thank you.